Now, Newton's theory of gravitation is not the last word on gravity. If you deal with very strong gravitational fields, Newton's laws start to become inaccurate and eventually illogical. And Einstein's general theory of relativity supersedes Newton's theory. The differences between Einstein and Newton's theories are immeasurably small for all normal situations, including almost everything we're going to meet in this astronomy course. Which is why we continue to learn Newton's theory. It's much simpler. But when we get very strong gravitational fields, such as near black holes, Einstein and Newton's theories diverge and Einstein's work better. Now, people, such as Stephen Hawking, are finding situations where even Einstein's theory is not working and are looking for something even better. Now, I want to talk here a little bit about space exploration. I'll talk a little bit first about rockets. Rockets are an example of Newton's third law in action. You heat gas very hot so it shoots out of the back of the rocket, and the reaction causes the rocket to accelerate forward. The difference between a rocket and a jet engine is that a jet sucks air or oxygen to burn the fuel, but a rocket carries everything it needs to burn inside, including oxygen, if that is the fuel it needs to burn. Most of a rocket is made up of fuel in tanks. As the tanks empty, they are dead weight and they are typically discarded. In older rockets, the engines went too, leading to multi-stage rockets. So for example, this is a cross-section of the Apollo rocket. The first stage, you had the two parts of the fuel, which was liquid hydrogen and liquid oxygen. You put them together, they create water, very hot water, it shoots out, and the rocket goes up. Eventually, these fuel tanks are empty and they're just dead weight that you don't want to try to accelerate forward, so the rocket brakes at this point and the second stage takes off. So today, when we launch a satellite by a rocket, it goes upward to clear the atmosphere, but then we have to turn on the side and boost the satellite horizontally to a speed of at least 18,000 miles per hour. So straight up, then turn around and shoot the satellite horizontally into orbit. If it's got the right speed and direction, great. If not, the orbit is in the wrong shape. And typically, the acceleration phase of a rocket launch only lasts a couple of minutes. So, if I'm here and this was my launch pad, and I launched it in the wrong direction, it would come up and it would come down. This is an elliptical orbit with the Earth at the focal point, but most of the Earth is inside this ellipse. So this is, say if I wanted to launch a missile to land somewhere else, I would take an elliptical orbit like this. I launch it, and then it's probably about here, its rocket burns out, and it just free falls to wherever it's going to land. If it's going too fast, it goes way out and comes back, and it'll go into orbit. It's an elliptical orbit. Most satellites, though, you want a nice circular orbit around the Earth, so you have to get it just right. Now, many satellites, including the space station, travel within a few hundred miles of the Earth's surface, so they take about 90 minutes to make one orbit. Higher orbits take longer. Remember Kepler's laws. So, for example, the Moon is 250,000 miles, and it takes a month to go in orbit around the Earth. An orbit of 22,000 miles above the Earth's surface has a period of 24 hours. So if you put a satellite above the equator at that altitude flying east at the right speed, it appears to hover above the same point continuously. These satellites are called geostationary satellites. They're the ones that we use for communication, like Dish Network or DirecTV. Since your satellite dish does not have to move. So they're in orbit around the Earth, but the Earth turns the same time that it does, and so it always seems to appear stationary above the Earth. Now, to escape the gravity of the Earth, say we wanted to go to the Moon or the planets, for example, you need to travel above 25,000 miles per hour. If you launch with a velocity less than that, you will always fall back to Earth or stay in orbit. By comparison, the minimum speed needed to go into orbit is 18,000 miles an hour. There is a mathematical relationship that explains the velocity that an object has to escape the gravity of a planet. You don't need to know this, but I just want to know the form. So the escape velocity is square root of 2, this is Newton's gravitational constant, so the mass of the planet divided by the size of the planet, or the radius of the planet. So the more mass, the harder it is to get away, or the faster your escape velocity has to be. So we've done this a few times. Deep space travel. Man went to the moon between 1969 and 1972. Spacecraft have landed on Mars and Venus. They have also orbited Jupiter, Saturn, and one asteroid. And spacecraft have flown close to all the planets except for Pluto. Now, if I want to get to another planet, I just don't point a rocket at the planet and shoot. What we have to do is put ourselves in an elliptical transfer orbit and then cruise there without power in an elliptical path. So, for example, as the Earth is going around the Sun and Mars is going around the Sun, if I want to get to Mars, what I do is I take an object above the Earth and I shoot it and I put it into an elliptical orbit around the Sun. And I do it at just the right time so that as the time it takes the object to get there, so Mars might be here, and as they come, the two objects will collide, and you want then them to arrive there at the same time. That's when they talk about a right window or a launch window, when we can launch from the Earth and get to Mars, because Mars has to be in the right position so that those two will come together. Now, there are two reasons to go into space to study astronomy. Number one, you can study the planets close up if we send a spacecraft up there close. But we can also just put telescopes into orbit around the Earth in order to avoid the Earth's atmosphere. This is important because ultraviolet, X-rays, and other wavelengths of light don't penetrate the Earth's surface. So this concludes Lecture 3.